Basic ones, indefinite ones. Why indefinite, Ryan? How can you tell just by looking at the first problem that, for those of you guys that came in late, we were working on at the beginning of class? Go. There are no numbers or bounds. Usually there are bounds in the bottom and in the top. There are none, so it's indefinite, which means, which means we're looking for, what's the snazzy term for the function whose derivative this is? We're going backwards to find. Louder. I think you said it, no? Well, we could say antiderivative. Ha-ha! We're going backwards. Antiderivative. We're trying to find the antiderivative. Remember, the dx is a bookend for the integral, basically to say, hey, it's legal as long as everything is in terms of x to go ahead and integrate in terms of x, which hopefully you guys did already. Let's go ahead and get the little pen. What rule did you use for the first one as I'm starting to write the indefinite integral solution?
Sum indifference and power.
Good. Sum indifference and then power. I'm not going to go ahead and write all the craziness out because that looks like a 9. The sum indifference just says basically you can take it one piece at a time, right, cool kids? Okay. We could do x to the 4th over 4. We could also do x to the 4th times 1. Sorry, x to the 4th, yeah, times 1/4. Basically, long story short, the 4 comes down. We can always check by taking a derivative. 4 comes down, cancels out, x cubed. Does that work for the first term? Perfect. So what did you guys get for the second term? Good. 1/2 x squared. Did you double check it? Take the power rule. 2 comes down, cancels out. The 2 becomes a 1. Haha, we got it. Right? Okay, we have one more term. Maybe, maybe not. But we have 1/4 x to the 4th plus 1/2 x squared plus, what'd you guys get or do with the 5? Nice. If you needed to look at those integration formulas, do you see the integral of k? And the integral of k is kx plus c. Or double check it. What's the derivative of 5x? 5. But you would not be done unless you plus c. Can you just pretend I box it and then we go on? Okay, cool. Letter B. What rules are you looking at? Trig rules. Sum and difference, you can still take them one piece at a time because there are 2 separate terms, so I can take 2 separate integrals. When I look at the first one, secant squared, when you looked at it, what should you have thought? Ooh, he is the derivative of, good, tangent. Double check it, but you have to know your derivative rules in order to be able to double check it. What's the derivative of tangent? Positive secant squared. We're good. Okay, second term. Did you guys write the minus and then take the integral? Okay, so write the minus because sum and difference. Now when you take the integral of cosecant x cotangent x, hopefully that makes you think, ooh, which trig? Cosecant, but if you're looking at just positive cosecant cotangent, then you would need to think of, there needs to be a negative. So we can do negative cosecant. Others of you might have just noticed, hey, there is a negative, so I can just make it a plus. Positive cosecant, but either way, however you think about it. You guys cool if I just go ahead and say, hey, minus a negative is the same thing as plus? Is that all right? Final answer, tangent plus cosecant plus c. Dun 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 dun, pretend I box it. Dun dun. Is that okay? How about number 3? It was a trick because these rules are not specifically on your basic integration table and you are going to see them in future sections. But for right now, what is the integral of 3e to the x? Good. You had to use the constant multiple idea where the 3, no big deal. He's chilling because he's multiplied. He's a coefficient. And then the derivative of e to the x is e to the x, which means the integral of e to the x is? Sweet. Don't we like him like a phoenix rising from its own ashes? You guys really didn't remember that quote when I said it last semester, did you? All right, that's fun. Francois Lyonnais, who has not been amazed to discover that like a phoenix rising from its own ashes, e to the x is its own derivative. There we go. That's how the quote goes. It was on our AD sweatshirt a few years ago. It was in our old book. It's not specifically stated in your book. Question, why did I put 4 times? Yeah, 4 is just a coefficient. I brought him out, but if I bring the 4 out, who's left in the numerator? 1 over x, oh my goodness, power rule. X to the negative 1, we add 1, we divide by, wait. It's a special case. It's the one that the power rule is illegal for. If you tried the power rule, you would have gotten divided by 0, which should have reminded you, uh-oh, somebody else has a derivative of 1 over x, and who is that somebody else that I'm writing? ln. Then I put a box around it. Don't forget your plus c. Dun, 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 dun. Dun, dun. How we doing? How many of you guys got 1 right? Ooh, 2 right. Keep them up. Ooh, 3. Nice. Show offs. All right, here we go. Let's keep going. Okay. Here's a couple of different examples. Now, this is kind of weird because, guys, if you look at this first one, it's not an integral. Who is he? What? Why are we finding a derivative? I'll show you in a second. There is a reason. If you remember from that table that we looked at yesterday, forever number 31, derivative rules have corresponding integration formulas that go backwards, right? So maybe that's what we're doing in letter A. I want to remind you guys really quickly what we do have to do with quotients when we take derivatives. So on letter A, go for it. Review the quotient rule. You're just taking a derivative. Ready, set, go. Court. If it was a limit, we could go to all the work of trying to plug into the limit as h approaches 0 of f of x plus h minus f of x all over h. But we have to make that whole thing. You know what I mean? Let's not do that. Let's not do that. All right, we're just doing an old-fashioned quotient rule, cool kids. I'm just trying to show you a point as to why we can't do quotients right now with integrals. And to do that, we're reviewing derivatives just for a second. Bridget, all you basically missed HCTV. We prayed for the rain and for safety and for, life. And then we did 3 quick examples of integrals. That's it. Welcome. All right, you guys just do it at your speed because, I'll take a little bit to catch up. If you're wondering why I'm doing old school, it's because I need an administrator password to get my iPad hooked up, and right now it's not working. But they're going to work on it today for me, don't worry. Bottom, do top? Minus top, D bottom. Don't judge my line. I'm working it. The line's still rough. All over bottom squared. Trying. Can you do quick mental math? X squared minus 2x squared. You guys hopefully worked it out. Negative x squared. Is that good? Plus 3. Hold on, don't go on yet. I have a point to the first one, even though I'm sluggishly coming behind you. You didn't make any silly math mistakes, did you? Oh, why am I putting an integral? That's messy. What am I doing? Okay, pause. Come back. Why did I write an integral? From a derivative. Yeah, I know, right? From a derivative. Can't we make an integration formula? Remember yesterday, guys, all those integration ones we were doing up here? Didn't a derivative formula result in a backwards integration formula? I mean, it's a forwards integration formula, but we can go backwards and we can make an integration formula, right? Same thing here. A forwards derivative formula, we can take that backwards, put the k in the integral, and we'll get kx plus c, of course. Same thing down here. Derivative of sine is cosine, sweet. Integral of cosine is sine of x plus c. So, what can we answer this integral formula with? I just simplified. my quotient rule. There's my derivative. What would be my original?
X over x squared plus 3 plus
Now hold on. I want you guys to think through with me. Yesterday, didn't we ignore any quotient E1s and we made them into sums and differences instead? The question is why? Let's pretend all of this stuff was hidden. If I can find my screen shade user somewhere. There it is. Let's pretend all the top stuff is hidden. Let's pretend this was the question. Would you be able to jump from here to here? No. How do you do a backwards quotient rule? And backwards quotient rule, remember stuff like canceled out? How do you know exactly what canceled out? Where did negative x squared come from? Maybe it was negative 4x squared and plus 3x squared. You don't know where it came from. Quotient rule backwards is much, 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 much more complicated than quotient rule forwards was. Integrals are great, and there are easy backwards formulas. However, quick heads up, quotient rule, product rule, there is no such thing as a quotient rule for integration. There is no such thing as a product rule for integration because, long story short, the quotient rule, a quotient ends up to be another quotient but with a subtraction and a squared and it gets all messy. And a product rule ends up being a sum. There's not going to be a product rule backwards for integration. There's not going to be a quotient rule. Now, there are ways of dealing with harder things. How do I get rid of this guy? There he is. There are ways of dealing with this guy, but not that we're going to see for quite a while. Okay? Corey, what was your question, bud? Oh, remember, this came from this positive expression. So when I take the integral of the negative, it's going to end up being the original. Does that make sense? Yeah. It's weird. All of that was basically to say quotients and products beware when they're inside an integral. If we can make them into sums and differences, our life is much better. Here's another beware. Beware of powers that are funny, but haven't we already had to beware of powers that are funny when we were taking derivatives? Oh, well, how did we beware? How did we help our mind, our brain out when we were dealing with roots? Rewrite it. Yeah, so keep the integral. Don't take them yet. The nice thing is, kiddos, with these integration formulas, if you keep the integral, you know you haven't solved for it yet. Derivatives, remember, sometimes we get lost. We would rewrite it, think we derived it, and we were done, and we weren't. Keep the integral. We haven't done anything yet. We're just rewriting it. Rewriting it to be 2/3 dx. Now, what rule do we use? Power rule, yeah? Now, hold on. Let's see if we can do this without writing it all out. To add 1 to 2/3, what am I going to be adding to make it easier on my brain? 3/3. Cool. What's 2/3 plus 1 plus 3/3? 5/3. Now, we could divide by 5/3 for the power rule, but ew, yuck. There's an easier way when you have a fractional power. I need, when this 5/3 comes down, I need the 5/3 to cancel. So when I divide by n plus 1 for the power rule, I'm going to multiply by the reciprocal. Now check it. Does this make sense? You can check any antiderivative, any answer to an integral problem by deriving. Power rule. We're taking a derivative to check. Bring down the 5/3. What happens to him? Psh, psh. He's gone. Perfect. There was no coefficient besides 1. Then you subtract 3/3. You get 2/3. Hey guys, does it work? Yes. We just need to finish by adding a plus c. Questions? Is it all right? Now, just in case you need to see it worked out, just in case, you can do this. You can do this work. I was just trying to help us think through it, mental math. Remember, the power rule says n, whatever the power is, plus 1. We made it plus 3/3 to make it easier on our brains because 1 is 3/3, common denominators. X to the n plus 1, all over n plus 1. We were making it easier on our brains. Plus c. This is the work we try to do in our heads. So technically we could go here, and then we could go here, and then we have our final solution. Cool? Beans? Sure? If you're alive, give a grunt. Alright, that was fun. Okay, so what would you do on this one? It's a product! Kind of. Why am I saying it's a product, guys? Yeah, how can you rewrite a square? 2 plus y squared times 2 plus y squared. Do we like products? Long story short, we don't like chain rule backwards either, because he gets hard. We'll see that in a future section. Long story short, we have nothing to help us integrate u squared dx or dy or dt. We have nothing yet. Nope, we can't do it. We can't do it. If we were doing chain rule, if it was u squared, we would need a u prime. We would need a 2y. I'm giving you guys a harder section that we're not in yet. We would need the 2y. We would need the u prime to go backwards. We don't have it. Long story short, even BC kids wouldn't be able to do this the hard way. They'd have to do what I am going to tell you to do. What you were going to tell you to do. How do we get rid of the multiplication? There's no other side. Multiply it out! Foil! Ready, set, go. Foil! Ready, okay? Yeah, okay. Just making sure. Foil it out, kiddos! We're just rewriting. We're not solving for an integral. We're just foiling it out. Why? Because I'm telling you, just got to trust me. I'm telling you, product rule, chain rule, the integration. Product rule doesn't even exist, and chain rule, there's a whole section we're going to spend multiple days, maybe even a whole week trying to figure out. Not cool. A simple foiling makes this so much easier and makes it basic. We'd much rather do basic than have to say it's impossible. When you guys foiled, what'd you get? 4 plus 4y squared plus y to the 4th. Real quick, have you guys noticed that when there's more than one term, there are parentheses in the integral? Do you know why? Good, to separate it. The dy needs to technically be with every single piece if you were to do it to integrate piece by piece along the sum and differences. All right, go for it. We did an example at the beginning. You guys worked through it slowly in your groups. Maybe some of you are getting faster. You shouldn't be writing down x's because everything is in terms of y with dy. Step by step, turn by turn, piece by piece. Can you integrate? Rebellious. Mr. Tooley is now doing chair by chair. We're trying to raise money to put stuff inside this room.
It's like going backwards. So, y. Like, what?
Isn't it just like this special, like,
No, I didn't. Well, I like that one a lot better.
It's like doing backwards to each one. So, what do you have to derive from it? Yeah, 4y with the rest. So the first one is 4y.
Did you say wait?
You're just going to add whatever the variable is. The next one is harder. What you do is you
how'd it go, Star? How'd it go? If you guys have not yet checked how far you've gotten with the correct answer, check it. Check me and make sure I'm right, but how do you check my answer? Derive it. Any integral you can check by deriving. It is a glorious thing. You don't need a back of a book. And you will practice your derivative skills at the same time. What? We're shooting for those fives. I want you guys to write down the next example. I'll tell you what I'm telling my Algebra 1 ninth grade kids, who are a lot of athletes.
Is there a lot tomorrow?
Yes, I'm planning on it.
Also tutoring this semester?
Yes, it's all at the front table. Do you want to pass it out right now? Thanks, kids. Stamp sheets are up there, tutoring hours are up there, and test correction sheets, which we don't need yet. You guys write down the next example. Kiddos, write down the next example because it introduces something new. Introduces something new. Slope equals square of the distance between the point x, y, and the y-axis. What? Okay, just write it down. I know it's a nasty word problem. It has something to do with all this integration stuff that we're doing. You might not even see anything like this in homework. I actually don't think you will see something quite this hard. But it introduces an idea. It introduces an idea. Real quick, as you guys are looking or writing, I'm going to go ahead and pull up the calendar so that we can talk real quick about what's coming up, especially when I'm gone. I don't know what it does exactly. Ooh, look, I have a pointer. I have a mouse. It's not very exciting. What else is it? Oh, it's kind of a bummer. Not as useful as I hoped. Okay. Lo siento for the quick me playing with the remote thing. That's not very helpful. Question. How do we translate this? Slope. Oh. Slope. Derivative. dy dx. Does that make sense? I don't want one. Slope. dy dx. We're translating into math. Remember, with any word problem, we always try to translate into math if we can. We did that with related rates. We did that with optimization. We even did that with motion. Slope is what?
Square
Square of the distance. Ew. Alright, well, square of the distance. Distance formula, remember that guy? That's disgusting unless you notice the square root squared. That's nice. Between a point x, y, and the y-axis. What's the equation for the y-axis?
X.
Close. The entire y-axis? Nope, that's the x-axis, isn't it? Hold on. We want the y-axis. So who is it instead? X equals 0. Wait a minute. So if we were to make a graph, put a random point, the shortest distance between any two things, the random point wherever he is in the x-axis, is what kind of line? Straight line. Struggle. Question, do I even care about the y's, or are the y's the same? The y's are the same, so all I care about is, hey, what's the difference between, wait, x value is the distance, isn't it? No. Well, that's dumb. X is the distance. But what we mean by that is, remember if we plug it into a distance formula, we'd have x minus 0 squared. And then we'd have plus y minus, but the y's are the same, so y minus y would be 0 squared. The 0 doesn't matter. Blah. The x squared will cancel out with the square root. And so actually, I know this is a really dumb way of saying it, and the nice thing is, this was on some like really old AP, hence where I got it. But the question isn't, can you perfectly translate that really convoluted way of stating that the derivative is x squared? The question is, do you know how to keep going and to find the original function given this clue? They want us to find the original. It wasn't explicitly stated. I think I left off probably part of the directions. But we want to find y. We want to find the original. The question, who do we have? dy dx. How do I go backwards from a derivative? Angela, Ella, how do I go backwards from a derivative? I need an integral, but I can't do an integral. I can't do power rule until I write it nicely. How do I write it nicely? Multiply the dx to the other side. I'm multiplying him up, so now he's gone. Now what can I put in myself, because I know how to go backwards? I need to put in an elongated s, which means an integral, right? And then on the left-hand side, do you guys remember what the integral is of 1 when you're talking about y's? Who has a derivative of 1? Y alone. If it was 2, it'd be 2y. If it was 3, it'd be 3y. The dy tells me make it with y's. I'm like, cool. Over here, x squared. He's the derivative of a cubed function, right? Because the 3 comes down, you subtract when you get squared. But who do I need chilling in front waiting for that 3? Plus c. We're done! No, we're not. Why aren't we done? What's new in this example? What was I trying to introduce to you? I can find c because I know an x and a y. And with that x and y, can't I just say, oh, fine, whatever, he has to work, which means plug in 2 as the y value. Plug in negative 1 cubed would be negative 1, that'd be negative 1/3. I plugged in the negative 1 as x, I cubed it and multiplied by 1/3. So from all of this, what does c equal? Nice, because 2 is 6/3. 6/3 plus 1/3 would be 7/3. And my final answer, if they want me to find y, is to plug it in, and be done. So y equals 1/3. You need to scroll down. X cubed plus 7/3. Plugging in the c. There is only one answer to this one, but what was different in the directions besides all the annoying translating stuff? They gave us a clue. They gave us a point, and we could plug it in, Now we're going to talk about that whole really quickly. Hey, remember, whenever they give us some sort of the snazzy term initial condition, we can plug in and find c. But first, let's look at one more tricky problem. Letter B. which technically is probably something like letter G in all of our examples, but obviously I wasn't really keeping track. Question. Is he in the table of formulas I had you write down yesterday? Some of you are going to think he is. But is cotangent squared an answer to any basic trig derivative that we know? No. Hence why cotangent squared is not in any of the integrals. Who is in there? Cosecant squared. Who's not in there? Cotangent squared. So he's impossible? No. It's not impossible. We just got to go back to who's been helping pre-cal kids the last couple days with homework. What are they working on? T-proofs. Trig identities. Cosine squared plus sine squared is 1. Why am I bringing that up? Cotangent squared is a Pythagorean property, and cotangent squared equals cosecant squared minus 1. Why am I bringing that up? Because he has an integral. He has an integral. He doesn't. But using pre-cal properties, being like, wait a minute, he doesn't have to stay like that. We can write him like, oh. So if we write him like this, using the Pythagorean property backwards, maybe some of you need to add some of those Pythagoreans to your forever card. Did we write them all down or just sine squared plus cosine squared? Lame sauce. Maybe you need to go back or just borrow a pre-cal kid's notes and look at their 5.1 identities. Pythagorean ones. Now we can look at our table and say, hey, who has a derivative of cosecant squared? Uh-oh, it's the C one. It should have had a negative. Let's put in a negative. Who has that derivative? Cotangent. And I still have this minus 1. Yeah, x has a derivative of 1. Plus c, dun 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 dun. Hey, a practical application, at least as far as this year in math and your success, just kidding. But your understanding of some of these tricky problems in calculus of your trig identities. Okay. All right. Ready? Last page of notes. And this one's quick. Basically, it's just saying how or when can we find C? We can only find for the value for a specific, the specific value of C. So remember, otherwise C is arbitrary. Otherwise C can mean any constant. We don't know. Every constant has a derivative of 0. Who knows? But we can only solve for an actual value of C, which is the arbitrary constant of integration, if you want the snazzy name, constant of integration, when given a particular point. When given a particular If we're given a clue, we can solve for C. If we're not given a clue, we leave him as general plus C done. A snazzy term or a snazzy way that the directions might indicate that it's one where you do need to solve for C. They could say something like solve the initial value problem. If you notice, it's very similar to what we just did, except you didn't have to go through all this convoluted mumbo-jumbo to get the actual differential equation. But think the convoluted mumbo-jumbo is actually saying, hey, there's a real life something behind this. But hopefully you guys, from the example that we just did, realize where we're going to be starting in a sense of to solve. We have to start with that derivative and we have to go backwards. When they say solve the initial value problem, or when they say something like find y, I want to find y, but I have the derivative, I need to go backwards. And the only way to go backwards is with an integral. We don't like that multiplication as we already talked about, so we're going to go ahead and do 2x times 2x times 2x, which is 1 over 8x cubed. Please, someone tell me how you can rewrite this to make your life so much easier? No, don't go taking an integral like that. That's illegal. Rewrite first. Rewrite. Pause. Does it make sense, my rewrite? It makes everything so much easier. I'm going to go ahead and integrate the left side because it's easy. What did I do with the 1 over 8, the coefficients? I brought them out. I had a 1 over x cubed. What's the only way to rewrite that to make it a power? Negative. Now can I do the power rule? Yes. I end up with y is equal to 1/8. Actually, technically, you guys see a negative 1/24 instead? Nope, not 1/24. 1/32. Nope, not 1/32. Struggle. I'm still getting used to integration. 1/16. Why? Because x to the negative 3, when you add 1, what do you get? And when you divide by negative 2, he goes joining that 8. If you don't believe me, double check me. Bring down the negative 2. What do you get? Positive 2 over 16 is 1 over 8. Ooh, yeah. Subtract 1, you get x to the negative 3. But we're not done, and why is that? When x equals 1, y equals 0. Remember function notation, f of x, they can say y of 1. It's the exact same idea. So what are we going to do with that 1, 0? Plug it in, plug in 0 for y. We have negative 1 over 16. If it's easier on your brain, you can do 1 over x squared, which is x to the negative 2. But we're just plugging in a 1 anyway, which is kind of anticlimactic because that's all just 1 times negative 1 over 16. Solving for c, add it to the other side. What is c? 1/16. And if they want me to solve the initial value problem, they want me to go all the way, which means y equals who? Plug it in, plug it in. Negative. If you want to make it pretty, it'd be 1 over, you can put that x down with the 16, the x squared, because it has a negative exponent. Then you have plus 1 over 16. You could have gone ahead and factored or whatnot, I don't know, yada, yada, yada. But that's one way of writing the one specific solution of the problem. You guys get the difference as to when's the only time we need to keep going from our general antiderivative? They got to give us up. All right, okay, sadly we are towards the end of class. So tomorrow at the beginning, after you guys finish working through homework tonight, before we even check the evens, we're going to do what? Integration competition in your groups. You're going to immediately, first thing tomorrow, you're going to get whiteboards, you're going to get markers from the front, and you're going to get towels, which are hidden beneath Christmas paraphernalia. Anyone on student council, please ask Becca where that goes, because I'm kind of tired of it. And we're going to get working. But we only have a minute. Kiddos, can we look at our calendar real fast? Okay. Here's today. Yeah, it looks a little different because this is my view of it. I've taken off all my other classes so you guys don't see it. Today we were supposed to finish section 4.1a. We did. We just didn't do the integration competition. We'll spend part of the class tomorrow on that. Tomorrow our homework on 4.1a is due. Don't worry. It's all on the homework sheet. I've selected the problems. We're splitting 4.1 into two sections for very good reason. Then we're starting on 4.1b, motion. Thursday I'm going to be maybe here. We'll see how that goes. I don't have to be at the doctor's till 1, but people are trying to tell me not to come, but anyway. Somehow, whether it's a video or whether it's me live, we're going to be keeping working on 4.1b, and I think on Friday, to be honest, I'm going to delay this until Monday, move your whole calendar over a day, or we'll figure out something or others, and I'll probably have Friday be a work day based on the 2 days of motion that you've gotten. 1 day with me, 1 day maybe with me, maybe with a video of me. Sound good? Okay, so Friday we're going to be working that way. This whole homework And there is a motion packet that we're going to be using in class to really go in depth in motion. We didn't with derivatives last semester. I think we need to kind of go over that. We're spending 2 days. You guys have a work day on Friday to get all that stuff done. Sound good? All right, cool kids. Thank you so much. I will see you later. Happy
When
Tuesday.
you keep deriving until you get down to 0 and then 0 again and 0 again, what's that called?
Um,